Okay, hello again. So now I want to talk about ideal or perfect gas law. This is just a reminder for you uh, because this is also important for some fluids problems. But just as a reminder, you should have studied this before, but I will give you what is ideal or perfect gas law. Sometimes you might, in some of the problems, you might use it just for relating pressure with temperature. So in general, the ideal or for an ideal or a perfect gas, the pressure is absolute pressure can be written as its density times R, which is a gas constant, times T, or the temperature of the gas. Okay, so P is absolute pressure. Rho is density, which is going to be kilogram. The units is going to be kilogram per meter cube. R is a gas constant, which is around, you can find it from tables, and we will give it to you if needed. T is absolute temperature. Just note that this is absolute temperature, and the unit of that is gonna be Kelvin. So it's not Celsius degree, Celsius centigrade, degree, or Fahrenheit. It is Kelvin. So this is how this formula works. And then I want to solve an example for you for this formula, so you get more comfortable with it. So example, at 40 degrees Celsius, the volume of a gas is 200 milliliter. The temperature of the gas gets raised to 50 centigrade with no change in pressure. So pressure is going to be constant. What is the question is what is the new volume of the gas? So what we are doing is we are just increasing the temperature of a gas, and if we want to see under a constant pressure what would be the new volume of that. Okay, so in order to answer this question, I'm gonna use ideal gas law. So the ideal gas law states, as we wrote it there, P equals to rho RT, right? And what is rho? Rho is density, so I can just write it as M, which is mass, over volume times RT, correct? So during this transition from 40 to 50 degrees Celsius degree, P and M do not change, right? And we know R is a gas constant, correct? So what I can say, I can take all the constants in one side of the equation and then see what I'm gonna have. So P is not gonna change, it's a constant during this transition. Based on what? Based on what has been said in the problem, right? With no change in the pressure. This is what the problem already has stated. Okay. And M is also not going to change. The mass of the gas is not going to change during this transition. We are not adding adding any gas, or we are not kind of having a discharge of any gas or any leakage of any gas from this volume that we are investigating. So it's also a constant, and R is also constant because it's a gas constant that is already in the ideal gas law formula. So I'm gonna take all the constant in one side of the equation. So I'm gonna have M P over M times R is gonna be constant, which based on this formula is what? Is gonna be T over V, correct? Temperature over volume based on this formula here. Just a substitution. So for these two states, one before at 40 degree and one at 50 degree, I can write this. Because this is constant, this has to be constant. I can write the first T, T1 over V1 should be equal to P over MR, which is constant, and this should equal to T2 over V2, correct? And the question wants the new volume of the gas, right? This is the V2. So we want to know what is V2. We know already what is V1, right? This is V1. We know T1. We know T2. And we want to know what is V2. Okay. So based on this formula, I can say that V2 is going to be V1 times T2 over T1. So I'm just going to substitute all the things, the known things here. So V1 is 200 milliliter. So I can just say it is 0.2 liter, right? Milli is, for those people who don't know, milli is 10 to the minus 3. Kilo is 10 to the 3. And these are some of the things like micro. We have micro. We might write is 10 to the minus 6. So these are some coefficients that you need to know in this kind of frameworks. So 0.2 liter, and then we have the temperature. But for temperature, it is given in Celsius degree. And we know here, based on this formula, this should be in absolute temperature. So what I need to do, I need to convert that to Kelvin based on this formula that is written here. So 1 Kelvin is 1 centigrade plus 273.15. So I'm just going to write that. So T2 is 50 degree Celsius here. So I'm just going to add it to 273 to get the absolute temperature. So I'm going to have 50 degree Celsius plus 273.15, which is going to give me the Kelvin value of that, over T1, which is 40 degree, plus 273.15. Okay? So if you calculate this, it's going to give us 0.206 liter. So V2 is gonna be 206 milliliter. So during this change, when we increase the temperature from 40 degree Celsius to 50 degree, and with no change in pressure, we see that the volume is also increased from 200 milliliter to 206 milliliter. So this is expected, right? Because you are increasing the temperature in a, for example, in the gas, and the pressure is constant, and so you expect that the volume should also increase, right? Because the temperature is increased, and that is what we obtain here. And the volume is increased by 6 milliliter compared to the original shape. Okay. So this was ideal gas law, or what we also call perfect gas law. And now I want to go to a new topic, which is more related to fluid mechanics, and that is viscosity. So viscosity is something related to fluids that are flowing. So two fluids can have almost the same density, but behave differently when flowing. This is a very important point. We can have two fluids that have the same fluid, the same density, but then one can has a very high viscosity, and one can have a very low viscosity, and they can behave differently when they flow. One can flow very easily, very rapidly, and the flow of the other one can be very slow, right? And this is what is related to the viscosity of that fluid. Okay, and here I want to better illustrate what is viscosity and better formulate that for you based on the stress and strain and strain rate in a fluid. Okay, and before doing that, I want to go back again to the definition of a solid, and also solid material and also fluid under a shear force or under a shear stress. Okay, so then you better understand the difference that here we have with solid mechanics in terms of this viscosity definition. Okay. So first, let's get started with this deformation of a material under a shear force P. Okay, so let's see how the material is gonna deform when we apply a force to that. Okay, so say you have a material here a solid material, for example, a steel or any other thing, okay? And then we have so let me color it. So we have like a fixed plate here. Okay. And then these are some properties of that. So this length is B. Okay, so what I want to do is I want to exert a force to this. Exert a shear force P here. So I am going to exert a force here. Okay. So what I expect is, if this is a material, if like a solid material, what you expect is that this material is going to deform and then stop based on the magnitude of the force. So I'm going to show the deformed material. Is going to look like something like this. Okay, after you exert this force, after you exert this P force, then this is gonna move, this side is gonna move around, say, delta A. And this angle is gonna be around delta beta, okay? So what happens is, I'm gonna write it down here. So the top plate would be displaced through small distance delta A, okay? So when you exert a shear force into this plate and onto the top plate will be displayed through a small distance delta A, okay? So now I want to show the force diagram of this top plate here. So if I plot the top plate again, draw it again, so we have this P force, which is a shear force. And then how it's stopped. There should be other forces that resist and does not let this top plate move, right? So we will have some And those forces are actually shear stresses that are kind of resisting, right? So I'm going to have some small shear stress here through this material that is resisting against that exerted shear force on the top plate, right? This is for a material, okay? And I'm gonna show that shear stress as tau, and this is something you have already studied in your solid mechanics course. And then if you want to show it as a force, you have to multiply it by area, right? Because stress is force per area. So this is going to be the force here that kind of is against that P force, the shear force, okay? And it's kind of balances that force so that the top plate stops moving further, okay? So for equality to occur, for equality of the forces to occur, and for it to not move, we need the sigma F to be 0, right? So the sigma of the forces should be 0 here. And so, because we have no movement, right? So MA is going to be 0. Thus, the pressure force, the P force, it's not the pressure, sorry. The P force, the shear force, should equal to tau times A, right? Where tau is shear stress and A is the area of the plate. Correct? So this is what happens when you have when you exert a shear stress on a material. Okay, but what about deformation of a fluid under the same shear force? And that is where we're gonna define viscosity. So let's see how that will be. So I'm gonna write deformation of a fluid under a shear force P. Okay? So the difference is in fluid, and here we had material, solid material. Okay. So let's see what happens now if I have this thing. So let me copy this one because this is the same here. Sorry. Not this. Let me see. No, it's not that, so. Okay. Yeah, it was not copied well. Yeah, I think it's better if I draw it. Okay. Yeah. Seems it's not copying everything, so let me just draw it again. So Here we have again the fixed plate at the bottom, but then at the top the things are changed. So the top we will have a moving plate on the top, and in between there is gonna be fluid between these two plates. Okay, so the other one, in between these two plates we had solid material. Okay, so let's see what's gonna happen. Let me just this is a fixed plate again. Okay, I'm gonna exert a P force again, like before. So what's gonna happen now is, now we are gonna have a moving plate. What do I mean by that? Because imagine you have water here. So let me just show it a little bit. Imagine you have water here. And these are just continuous, okay? I'm just showing a cross section here. But these are continuous. Imagine you have fluid here, and then you exert this force. What's gonna happen on this on top plate? It's just gonna move, right? It's not gonna stop. If you have a force, you just exert that, like any amount of force, it's gonna move. Okay, so on top, we are gonna have, instead of, unlike this one that was gonna deform and stop there because we had a material in between, not a fluid. So we are gonna have, this plate is gonna move. So we are gonna have a velocity, which I'm gonna show it with U. This plate is gonna move with a velocity as U. Okay. Again, this I'm gonna show, this is B, the same thing as before, this length. But what's gonna be different is this velocity. So the velocity at the top, the plate, is gonna be U, but the velocity at the bottom here, so I'm gonna show this profile so you understand it better. So the velocity at the bottom here is gonna be 0. Why? Because this is a fixed plate. So this plate, the bottom plate, is not moving, but the top plate is moving with velocity U. So the top plate is a moving plate and the bottom plate is a fixed plate. So if I want to show the velocity profile in this fluid, it's gonna be something like this. It's a linear change. So the velocity is gonna decrease linearly to 0 at the bottom plate because it's a fixed plate. We have kind of fixed it to something. And we just allow the top plate, the moving plate, to move because of the shear force that is exerted on that, okay? So let me write something. So this, I'm gonna investigate it now. So for fluids, or for a fluid, there is nothing to stop it. So when you exert a force on it, the top plate moves continuously with a velocity u. Okay. And the fluid between two plates moves with velocity u as a function of what? As a function of this y, this coordinate system. So if you have y here, this is y, and this is x direction, okay? So it's gonna move as a function of y. As you see here, it's gonna be 0 at the fixed plate, and it's gonna be equal to u at the top plate. If it changes linearly for this particular condition, we can write the velocity of fluid as this. So u is gonna be what? It's gonna be u, capital U, times y over b. This is just a formula of this profile. And we can check it. This means when y is 0, meaning we are on the fixed plate, then u of 0 is gonna be u times 0 at over b, which is gonna be give me 0. So the velocity of the fluid at the fixed plate, right at the top of the fixed plate is gonna be 0, which is what we expect, right? It is 0 here, as you see. And at the moving plate, y is gonna be what? Is gonna be b, right? Here. So we are at the moving plate, and so u at b is gonna be u times b over b, which these two are gonna cancel out, and so the velocity is gonna be u, and that is what we expect, right? Because the velocity of the moving plate is u. Okay, so this formula is consistent, and anything in between is gonna change linearly, and that is actually the formula of this linear change that I showed you here. Okay. So in the next lecture, I'm gonna define a velocity gradient based on this. So I'm just gonna draw it based on this shape. We can define a similar thing to a fluid, but with velocity. So this is delta A. And this is delta beta. Okay. So in the next lecture, I'm gonna define the velocity gradient based on this. And then we are gonna define a viscosity based on this deformation for fluids, and then define different types of fluids like Newtonian fluids, which will have a linear change between shear stress and rate of shear strain, and a Newtonian fluid. Okay. So let me just have a brief overview of what we learned here in this session. So we started talking about ideal or perfect gas law. So this is the formula of the ideal gas law, which is P equals to rho RT, which is absolute pressure equals to density times the gas constant times absolute temperature. And absolute temperature means we have to calculate it based on Kelvin. And then we saw an example for this where we raised gas temperature from 40 degree to 50 degree, and then we had the initial volume of that gas, and we wanted to find the new volume of the gas. Okay, so we use this formula to find a new volume of the gas based on the ideal gas law, and we found that it's increased during this increase in the temperature. And then we started the new topic on viscosity, in which we said that two fluids can have the same density but behave differently when flowing. And so we examined the deformation of a material where under a shear stress force compared to deformation of a fluid under the same shear force. So in a material, when you have a material, the top plate will be displaced through a small distance delta A, and then it stops. And so because of the shear stresses that are exerted in that material. So here we have a material, okay, just so you know, like a solid material. And so we wrote that in order for the equality to occur, the force should equal to tau, the shear stress, times the area for this solid material. But for a fluid, when you have fluid between two plates, the top plate is gonna move continuously because there is nothing to stop it. Okay, so the top plate here is gonna move if you have fluid inside here, like water, with a velocity u. And then based on that and the fact that the fixed plate at the bottom is not going to move, so the velocity of the fluid near the surface here should be 0. We wrote if the velocity profile of the fluid changes linearly, then the velocity of the fluid at each point based on this coordinate system should be u times y over b. So this means at the bottom it should be 0 and at the top it should be u. Okay? And so in the next lecture, I'm going to use this and continue on this deformation of a fluid under a shear force P, and then define velocity gradient because these are going to, as you can see, it's going to create a velocity gradient in y direction. The velocities are not the same, so we will have some velocity gradient, and then define viscosity of the fluids based on that. And after that we have defined that, we are going to solve one example of it, and this will be the end of chapter 1, and after that we're going to go to the fluid statics, which is the chapter 2 of the course. Okay, thank you very much, everyone.